Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on Foundational Mathematics, we want to start to talk about multivariable calculus, or calculus of many variables. So before we get started, I will just explain of the whole concepts that we will be actually going throughout this discussion. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description for the notes for this entire discussion. So we will mainly talk about two things. First is obviously differential calculus. So we'll go back to the idea of differentials such as derivatives as well as min-max problems, and then also we'll later deal with of the max-min problems with constraints, which we'll later discuss as of the Lagrangian multipliers. After that, we'll later talk about integrals. So this will be integral calculus of many variables. So integral calculus of many variables will later discuss about how do you take a area integral or a volume integral, but mainly we'll deal with area as well as the change of variables. And alongside with that, we'll also talk about how do we actually compute the Gaussian integral, which I promised on the last video. So that will be something that I will be explaining throughout this entire video. So if you want to skip out throughout this entire discussion, you could just refer to the timestamps written here. We can go and start to discuss about differential calculus of many variables. So for differentials in here, we'll be mainly concentrating with only two variables. So this logic could be implemented for multiple other variables, but in here we will just only discuss about single variable calculus. No, sorry, two variable calculus, which is pretty much already many. So let's start to actually think about the same idea as before. What if we actually take a very small change with respect to x, let's say. So if we have something like this, subtract that by this guy, x0 and y0. So what will this be? So this is something which is something which we normally call as the change in the f. But if we divide this entire thing by the change of x, then you take the limit as the change of x goes to 0. So this is like a refresher. This would end up being the derivative of f over the derivative of x. So the logic is very simple, in which if you have a multivariable function and then you want to find the derivative with respect to x, that means you treat all of the other variables as constants, and then you could just do the derivative. So there's also another notation of this, which is fx. This is a notation which I sometimes use, since it is very useful to write things in a much more cleaner fashion. Something like if you write it within LaTeX. So this pretty much straightaway introduces us towards the idea of differential straightaway, like the Taylor series, in which we introduce it as something like this, right? This equals to the function of x0, y0, plus the derivative of f with respect to x at that particular point, multiply that by the change of x. But what if we also change the y? So maybe if you just change the y, you would have the same formula but with different stuff. But what if we actually do this for let's say x and also y? So what we'll have is this change in the x as well as in the y direction. Subtract that by function x0 and y0. So what we would actually obtain is that you could actually add this with function x0 plus delta x point y0, subtracted by function subtracted by function x plus delta x point y0. So it's pretty much the same thing as we have already done. Unlike the differential calculus, what we'll obtain is that you could actually pair this up and this up. So what you would get from here is gonna be the derivative of y times delta y. Does it make sense? it pretty much makes sense because we are changing the y. And then you could add it by this guy, subtract that by this guy, which is the change in x times the change of x. So this relation is the key idea when you're dealing with multivariable calculus, is that if you have your change in your positions, let's say if it's a vector within one direction, and then you could split those changes into these two components, you could just do this to obtain the approximate change, or basically the differential of your function. So we could also try to discuss about the second order derivatives. So there is function xx, which is obvious, function yy, which is also obvious. You just take the second derivative twice with the same variable. But what about function xy and function yx? So in here, the way that I will denote this is that you take the derivative with respect to x first, and then you will take the derivative with respect to y for this one. And for this one, it's y first and then x. So it's pretty much something simple, in which you take the derivative of x first and then y, and then there's the other one in which you take the y first and then the x. But there's something interesting when we are dealing with continuous functions. So we could just actually try to think of this function xy first. So this is the derivative of x. So you take the derivative of x first, and then this derivative, you take the derivative of y. So if we try to write the definition, this is going to be function x at x0 point y0 plus delta y. Subtract that by function x of the function x0, y0. So this is something which you could get straight away, and taking the limit as delta y goes to 0. Now, with this, what exactly is function x? Function x is just the derivative with respect to x. So we could just rewrite this much more further. The function of x0 plus delta x and y0 plus delta y, because this is what we are interested in, the y. It's within this y0 plus delta y. We could subtract this by function x0 plus, and y0 plus delta y. Everything is divided by delta x. And then you subtract this by the function of the same thing again. It's x0 plus delta x point y0. That's the difference, minus function x0, y0. Divide that by delta x. Everything divide that by delta y. Now what I can do with this is that I could actually rearrange everything. So we could get function x0 plus delta x, y0 plus delta y, minus function x0, y0 plus delta y, minus function x0 plus delta x point y0, plus function x0 and y0. Everything is divided by delta x times delta y. So this is a simple idea, right? But if you are clever, you can actually just combine this guy and this guy straight away. So if you combine those two, what you would get is this is the derivative. This is the derivative of y at x0 plus delta x, comma y0. Subtracted by the derivative of y, so this guy and this guy, x0 and y0. You divide it by delta x. So this is fyx. So this is a very cool relation in which if you have a continuous function, you could do something like this. And this is very important, that the way that I write it like this is that this only works if the function is continuous. And why is that the case? If the function is not continuous, what you would have, the x plus delta x comma y0 and the function x0 comma y0 plus delta y would have totally different counterparts, in which if you move delta x first and then delta y, it corresponds to a certain function, but doing it the opposite way could correspond to a different direction. So this literally only works when the function is continuous. So this is something that you need to keep in your mind if you want to use this kind of property of the symmetry. So with this idea, we could actually just define the entire spectrum of taking the Taylor series. So we have the Taylor series of multivariable. This will be the function x0 point y0 is going to be, so function x yx is going to be function x0 comma y0 plus the first derivative times delta x plus the first derivative of y with respect to y plus the half, which is what you already gained from your Taylor series, and this entire function of all of the different combinations. It could be fxx, fxy, fyx, and fyy. So it's delta y squared in here. This is delta x squared. This is delta, oh sorry, this is delta x delta y. This is delta x delta y. And this is delta x squared. So you could just combine the entire thing and you would figure out that fxy and fyx is the same, so you would have this guy to be 2 times fxy delta x delta y if your function is continuous anyways. So this is a pretty cool idea when you're dealing with Taylor series. So we could actually expand the idea of Taylor series much more into a min-max problem. So remember when we try to do min-max problem, the way that we do it is that we try to find stationary points. Points in which its gradient is 0. And we could use the same idea when we're dealing with multivariable calculus. So if we want to take the change of f to be 0, of fx delta x and fy delta y, for any point, for one point with no matter what the delta x and delta y is, the only solution that this is possible is if function x and function y are both 0. So this is pretty important since this is where there's no change in the x and there's no change in the y. So it's not changing within any of the directions, if it is continuous anyways. And this will later result in 3 different kinds of functions. It could be a minimum, it could be a maximum, a local maximum, or it could be some form of a saddle point, in which it is like a Pringles, in which it's like a saddle. So there's like this hill as well as this valley combined within one surface. So the way that you would actually try to determine which one is min, which one is a max, is actually going to be explained much more when you are starting to deal with the matrix ideas. So in here, I won't fully discuss about how do you determine which one is minimum, which one is maximum. So you could just figure it out on your own. So maybe when you're dealing with min-max problem, something that you always remember is that what you normally find is always the local maxima or the local minima. But when you're dealing with real life applications, there's normally something which is like there's limits, there's constraints in which where you could actually tune your entire system. And this is where the idea of Lagrange multipliers comes in. So how do I actually explain Lagrange multipliers is something like this. Let's say if you have a function and this function is a function of x and y, and you want to try to min-max this function. But the way that you would need to solve this is that there's some constraint that is placed within your system so that this function has to always equal to a constant or maybe even 0. Now with this addition of this constraint, you couldn't truly try to find where exactly is the minimum or the maximum within your entire system. It's very hard for you to find it because normally what you figure out is that the maximum would be probably inside of this entire domain, while the constraint is putting you inside of a line. So to do this, we should try to remember what is the idea of min-maxing. So min-maxing is if you take your function that you are trying to analyze, take the derivative of it. This will be function x delta x, dx technically, and function y, dy. So with this differential equation here, you want this guy to equal to 0 because you don't want any change. So with no change, this means that you are within a local maxima or a local minima. It depends. And you could actually figure this out. So the value would be function x over function y is d negative dy over dx. So this is the first idea in which you could actually figure out that the ratio of the function, of the derivative of the functions, will correspond to a certain direction for it to be maximum and minimum. But this doesn't really help when you have constraints. So how do you use this information for you to solve this min-max within this constraint? We could also think of this g function, which is always, if you take the derivative of a constant function, is always going to be 0. So this thing is always 0, no matter what the condition is. And this value here is going to be gx dx plus gy dy. Therefore, we see a relation. Negative gx over gy is going to be the negative dy over dx. So we got this equation. Function x over function y must be equal to g of x over g of y. So maybe we could just state that each of these ratio corresponds to, let's say, no, sorry. So we could just try to restructure everything into function x over gx equals to function y over gy. So we pretty much group all the derivatives into one single equation. And let's say this ratio is, let's say, lambda, in which lambda is what we call as the Lagrangian multiplier. So this is the ratio of the f as well as the g, in which one of these lambda corresponds to a stationary points. So with this, we could actually restructure our entire thing. Function x equals to lambda gx. Function y is lambda gy. And the g must be 0 because that's what we already have. And if we solve these three equations, you could just figure out what's the stationary points for your function. And you could figure out if it's a minimum or maximum just by putting in your stationary points and then figuring out if it's minimum or maxima. So this is a pretty useful notation. You could also write this as the derivative of f equals to the lambda of the derivative of g. That also works. But maybe there's something in which we could actually use that is much more useful for us to write. So you could, instead of rewriting this entire equation, we could just define a new function. So if we try to define a new function in which we call this f to be equal to f minus lambda g, you just need to find what is the min-max of this. Just figure this out straight away and you would find your solution. So it's like you transforming your entire function straight away. So you would have the df to be 0 and your g to equal to 0. So that's the idea. So after you have already figured out about this entire thing, maybe we could add some more ideas. Maybe if we have multiple constraints. So if we have multiple constraints, we just need to add much more Lagrangian multipliers. So if we add another constraint, g2 equals to 0, what we could do is that we could just use our previous min-max problem, subtract that by the new Lagrangian multiplier. Or this is pretty much f minus lambda 1 g1 minus lambda 2 g2. So g is your constraint, the subscript corresponds to which constraint, and then lambda corresponds to the Lagrangian multiplier for that particular function. So now we can jump into the idea of integrals. So within integrals, the idea is, how do you actually try to find the integral of a multivariable function? So here's a very clever idea, in which we'll just try to use the same definition as we did from from what we learned from single variable integrals. So instead of 2 dimensions, we'll just play in 3 dimensions, in which we have x, y, and our function xy. And let's say it has a surface. So if you are interested within a certain area, you could just take small pieces of this area and try to sum them all up to get the volume. So this notation could be written as the integral of your surface D of your function x, point y, dx, dy, because we're taking small changes in the x and the y. So this is the idea of integrals. And how do you compute this algebraically? Is that you just need to get the coefficients. So it's like y1, y2, x1, x2. But these are a function of y because we are changing the y's as well. So there will later be an example of how do you compute using these multivariable integrals. So this will be fx point y dx dy. So you just need to take the inner one and then take the outer one. So let's just do an example straight away. Let's try to figure out the area of a circle. So we have already done the area of a circle, but we'll do this in a multivariable way. So for area, your function x point y is normally 1. So it will be just the double integral of dx dy. So if we have this circle, let's say the x squared plus y squared equals to r squared, how do we figure out what's the area? So we could just do summing up of the y. So we will just take this and then we sum this guy, and so forth. So this will be from negative r towards r. So that's what we will put on the limits. What about the x? This is where you need to be a little bit more clever. So let's use red in here. So for a particular y, let's say in this line here. Oh, okay, that's fine. At that particular arrow, we need to figure out what's the boundaries. So there's value from here until the value here. So these 2 points are our boundary. So we just need to solve for this positions. So we could just write this as the square root of plus minus the square root of r squared minus y squared. It's the same boundary. So this will later be the limit from negative square root of r squared minus y squared and the square root of r squared plus y squared. That's our boundaries. And then you just need to take the integral of this. So take the integral of the function, it's going to be x. So if you put the values, it's going to be 2 to the square root of r squared minus y squared. Integrate that from negative r to r of dy. And then you could do the same thing, but this time with respect to y, what you would get is your pi r squared. Exactly the proof so that the area is pi r squared. So before we start to get to the idea of changing variables, I also want to introduce a very unique property when you have something which you call as a separable function. So if your function x point y could actually be decomposed into 2 factors, xx and yy, what you could do instead is that you could actually take 2 different integrals outside of each other, something like this. And you could actually prove this very easily, because if you take the integral with respect to x, what you would get instead is that you would put dy outside. And then you would later do the same thing, would do the same integral anyways. So it's just one function multiplied by the other function. You could integrate them both. It still works. It doesn't change the result. So going to the change of variables. So I will introduce some coordinate systems first, and then I will teach you about changing the coordinates in here. So one very useful coordinate system when you're doing 2-dimensional systems is polar. So you might know polar to be r to be equal to the square root of x squared plus y squared, and then you would have theta to be the arctangent of y over x. Or you could just denote this as well as x equals to r cosine theta, and y is r sine theta. So with the system, you basically take, let's say, this guy here. Let's say if you have a point, you could just express this length as r and the angle to be theta. That's the idea. It's so simple. So the way that you could actually prove this straight away is that it's pretty much just trigonometry. If you want to take the x component here, you would just need to take the cosine and then multiply that by the hypotenuse. Same thing with the y direction. So how do we change units? This is where we need to use Jacobian. So remember last time in which I introduced, if you take a function dx, this must be equal to the integral of the function of u now with the Jacobian of x over u du. This is the same idea, but instead of u, you would do this with area. So the area that you normally use is dx dy. And then you want to transform this into dr d theta, because that's the variable that we are using in this scenario. So what's the Jacobian in here? So there are ways for you to actually figure this out. One way is to actually use a formula, which I will later give and also prove for 2 dimensions, but not really for 3 dimensions. And then also, what I will do right now is by using geometry. So let's do it with geometry. So if you take a very small r, and you also take a very, that's a small theta and a small r, what you could get is that you would have this small area. So the small area here, which I will just draw this in a much more bigger scale, this would be our dr, which is the small length in the r direction, and this side here. So what about this guy? If you think about it very closely, this is like if you take this guy here and then take this length here, or pretty much taking this length. It's pretty much the same thing in the end. So you're pretty much trying to find the arc length here. And if you know about the arc length, it's just r d theta. R times the small change in theta. So your area is gonna be r dr d theta, or you could do it r d theta dr. Changing the order doesn't really matter. So your Jacobian is gonna be r. So you could just write this as the j of xy over r theta is gonna be r. So that's the proof by using geometry. But if you want something much more sophisticated in which you're dealing with the vectors in general, what you could have is something like this. So if we have, let's say, 2 different units, this guy and this guy, to be our 2 new variables, you could add a small change as well as this guy has another small change. So this is going to be your delta U. So there will be a change within those 2 variables. And so this will be something which I'll call as A, and then another side will be B. And so your vector A and B could be written as the partial x over partial u in the I direction plus the partial y over partial u in the j direction. So this is like if you, so this is going to be expressing, if you take a small change in your u, what will be the effect in your entire system when it is converted back to xy. Same thing with the b, it's going to be partial x over partial v I hat plus the partial y over partial v in the j hat. So this is technically times delta u, and this is delta v. This is your new length anyways. And so if you try to figure out the area, or it's pretty much the cross product if you're doing vector calculus, the cross product here is going to be partial x over partial u times partial y over partial v minus partial y over partial u times partial x over partial v. And this is pretty much the absolute value of this. Multiply that by your du dv. And this entire thing is your Jacobian for xy over uv. So this is changing your uv into xy. This is the multiplier that you need. So you could use this for the polar system, in which you would have the unit to be r equals to x cosine theta and y equals to r sine theta. So if we denote this to be our u and this is our v, what you would get is for partial x over partial u, it's going to be cosine theta times partial y over partial v, it's going to be r cosine theta. Subtract that by the partial y over partial u, or the sine theta. Multiply that by the derivative of this guy with respect to theta, negative sine theta, times r. And this is going to be r, because cosine squared plus sine squared is 1. And this is our Jacobian. So those are some of the most peculiar ways for you to actually change variables for any kind of systems within 2D. And so now we will go to 3D, in which I won't fully express the entire conversion from any unit to any other unit. Instead, I will later explain about that when we start to talk about matrix theory. But for now, we'll just stick with the conventional systems. So there's the cylindrical system as well as the spherical. So the cylindrical system is a system of pretty much polar coordinates, but you add a z-axis. So it's, if you have, let's say, a 3-dimensional plot, if you say you have this point here, you just need to drop it towards the xy plane. This is xy, z, and then you just need to take this distance here. So this is z. So this is rho, and then the angle from here to here, we'll call that as phi. So it's pretty much just the same idea as before. So your x equals to rho cosine phi, your y equals to rho sine phi, and your z equals to z. And how do you figure out this change in volume? Because we're now talking about 3 dimensions, that means we need to play around with the change of volume. So it's pretty much just the same idea as before. Something like this. We know what the area is. It's r d rho d phi. So it's rho d phi. And the height is dz. So the Jacobian is going to be rho. It's pretty simple. So the other popular system is the spherical system. Spherical. So we'll use the same idea, but it's almost the same idea as the polar coordinates, but instead you're only expressing the length by only one value. So the distance from here to here is something which we will call as r, or the distance. And then the drop from the z-axis is what we will call as theta. And so you could drop this into the xy plane. So this is your rho as before, and your phi, if you remember. And just by using this, you could express new functions. So it's just it's just r equals to the square root of rho squared plus z squared. It's just a polar coordinates inside another polar coordinates. But it's expressed much more as x squared plus y squared plus z squared. And then for the theta, it's it's gonna be the inverse cosine of the z over r. And the phi is gonna be the inverse tan of y over x. So it's something that we have seen before. So the inverse, so the arctan of y over x is already something which we already know. This part is something which in which we have already know, but the theta is something a little bit different. So we could actually convert this entire thing into your x, y, z system. So x, y, z. So we could just cheat off from the polar coordinates. So instead of z equals to z, you could actually get something from this function. So it's cosine theta equals to z over r. That means it's r cosine theta. And so the rest is going to be rho, which is, the rho is r sine theta. And then you could use your rho by cheating off from the top. What you would get is, this is going to be r sine theta cosine phi, and r sine theta sine phi. This is your spherical coordinate system. Now, what about the Jacobian? This is where a little bit of trickery comes into play. So let's try to sketch this in a very elegant way. If we do something like this, does that work? No, let's just do it like this. Yep, like that, and then there's some bit like that. Okay. So let's say this is one part of our small volume. So this is going to be converging towards one certain point, or like the solid angle. So there's going to be the change in theta, there's a change in phi, and distance rho. So what's the area? Sorry, what's the volume? So it's just half times base time. No, sorry, it's base times height times width. So we're just approximating this to be a, not a cube, but a block, a orthogonal block. So there is this small, so let's say this is, so pretty much the width, length, and height is pretty much arbitrary for you to figure out which one is length, which one's width, which one's height. But we could say that this unit in here is going to be your change in rho. So that's one of the sizes that we need. So we should also try to think of this length as well as this height. So we should just think about the height first here. So the length of this guy is pretty much coming from theta, right? So from that theta, oh sorry, so this is technically r. So this length is gonna be pretty much just it's pretty much just a small segment of the entire circumference. So it's gonna be r sine, no sorry, it's r d theta. So that's the one that's going down, something like that. And then, like, what about this small length going this direction? It's not really r times the phi, because the length from here to here is, so sorry, from here to the phi, it's not exactly r, it's instead rho. So it's actually rho d phi, or it's r sine theta d phi. So what we get is that if you multiply everything, your Jacobian is going to be r squared sine theta. So this is your multiplier when you're transforming xyz into your r theta phi system, or your spherical system. So sometimes these kinds of manipulations of the unit is going to be very helpful if you're doing integrals of like very hard integrals in which there's no algebraic solution, there's numerical solutions instead. So this is a very useful tool that you could use to convert between your values. So that's pretty much all of multivariable calculus, but we could actually use the idea of multivariable calculus to figure out of something of the solid angle, in which I introduced a little bit on general physics 1, but I didn't use it that much. So the solid angle, or pretty much the steradian, is pretty much a counterpart of the angle, or the radian. So how do you prove that the total steradian of a solid is pretty much 4 pi? So we'll just use this idea first. If you have a circle, and then let's say there's length r, you know that the angle is going to be ds over r, in which the s is just a small part of this entire length. And then if you integrate this s, what you would get is the area over r. No, sorry, the circumference over r, which is 2 pi. But this usage is not really general. So for arbitrary loops, what you could state is that the d theta is going to be ds over dr cosine gamma. So this gamma corresponds to the difference in angle between the tangent as well as the actual. So it's like the tangent of the r vector and your entire surface. Or you could actually explain it by using normal vectors. So let's say if you have some weird loop, you have this r, and then you're going towards this direction. So this is the one from your circle, and then this is the path. The difference in there is what you call gamma. So if I draw something perpendicular, let's see if I can draw something perpendicular. There you go. This is going to be your gamma. So just putting your gamma in, do your integral, the answer should be 2 pi. That's something general. And that's pretty much the definition of radians. It's just a number that directly corresponds to angle. So what about steradians? So we'll use the same idea, but instead we'll just talk about the sphere with radius r. And let's say a small surface of this guy is d big S over r squared. This is your solid angle. So if you take this integral, and pretty much if you do this for a sphere, you know this to be 4 pi r squared, which you could prove just by figuring out the volume and then try to find the rate of change with respect to r. You would get the surface area. And so the surface area is going to be the one that you put in, which is 4 pi r squared. So in total of the d omegas, it's going to be 4 pi. And this is your definition of steradians. And the same logic if you have, let's say, a arbitrary shape or arbitrary surface. You know that if it is closed, your surface is going to be ds over r squared. Multiply that by cosine gamma. So what exactly is the gamma for surface as well as a tangent function? It's pretty simple. So if you have a surface and another surface, all you need to do is to measure out its normal vector, figuring out what the gamma is. It's just that simple. So this is why I explained a little bit about the tangent vectors, and it is because of this, because actually the change of the plane, the angle in between planes are very easily described by the angle of the normal vectors. So that's about the solid angle as well as the steradian, a very useful unit when you're describing solid surfaces. Finally, I come to the point where I need to fulfill my promise of talking about the Gaussian integral. Gaussian integral. So here's the idea. Let's say the Gaussian integral is defined to be I of a, which is the integral from 0 to infinity, e to the power of negative a x squared dx. So what does it mean if it is related to multivariable calculus? Here's the crazy part. Let's just actually, because this function is an even function, we could just extend it towards negative infinity as well, and it's going to be twice the value. Negative infinity towards infinity of e to the power negative a x squared dx. So it's symmetric. Even, so if it goes to negative, the integral will be the same as the one going positive. So it's fine. It's still the same integral, but, well, technically it's not the same integral, but you get the point. So this doesn't really help us with anything. We still couldn't solve the integral. But what if I actually multiply this by the same integral? So if we try to multiply this, again, what we'll get is something like this, e to the power a x squared dx, and also another variable, in which let's just call this as y, for no reason. And so with this, you could actually combine them all into these two integrals from our property of separable functions. This is going to be e to the power of negative a x squared plus y squared dxy, dx dy. Now we could use a change of unit. Let's just turn this into polar coordinates. So your integral is going to be, let's do dr d theta. So it's going to be e to the power of negative a r squared, multiply this by r, the Jacobian. And what about our boundaries? Well, for radius, it's going to be from 0 to infinity, so it's pretty much just the whole plane. And then your theta is sweeping out the entire field, so it's from 0 to 2 pi. So this is an integral that you could solve. It's e to the power of negative a r squared over 2ar, over negative 2a, yeah. Evaluate that from 0 to infinity, and then there's still another integral from 0 to 2 pi. So later the 2 pi would pretty much cancel out. The 2 pi is going to go out because there's no function of theta inside the thing. But I'll just leave it here. So it's going to be the integral from 0 to 2 pi of, putting the values in, e to the power of negative a r squared, it's e to the power of negative infinity. So it's going to 0. And then putting 0 in, you would get 1 over 2a. So this is going to be pi over a. So that's 4ia squared. That means you know what the ia is. The value is going to be exactly half to the square root of pi over a. And this is the value that we expressed when we tried to figure out what's the Gaussian integral. And also the use of the dummy variables to take the derivative, or the Feynman, or the Feynman's technique. So this is a very useful tool when you are dealing with, let's say, complex functions. You could just think of, I cannot solve this straight away. Maybe I could solve it with multivariable calculus. And it turns out that for this problem it works. So it's a pretty useful identity for you to remember when you're dealing with multivariable calculus. So that's all for today's video. I know that this video is mostly repeating on derivative as well as integrals, but utilizing it within multivariable calculus. So with that, I would like to close this video. So thank you very much for watching, and make sure to like and subscribe, and also please share this to your friends who really needs to understand the mathematics behind physics in a much more clearer understanding. So thank you very much, and I will see you on the next video.